Yeah.
Welcome, everyone, to this session of Shadow the Scientist, Chasing Asteroids with J.D. Armstrong. My name is Jamika Marshall, and I serve as the Shadow the Scientist coordinator. I'm so pleased that you all are here with us for this session. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. Shadow the Scientist offers free online public experiential learning sessions with professionals throughout various STEAM fields several times a month. You can scan the QR code here on the screen to visit our website where you can register for an upcoming session, request a dedicated session, or request to host a session. Our website is updated regularly. Now, in this session, we have the privilege of shadowing J.D. Armstrong of the University of Hawaii's Institute for Astronomy, or IFA, in Maui, as he uses the Las Cumbres Observatory network. The University of Hawaii is located in the most diverse community and environment in the world. They are a globally recognized center for learning and research. The Institute for Astronomy's mission is to advance scientific understanding of the origin and the nature of the universe by conducting high-impact research, developing new technologies to observe the cosmos, defending the planet from potentially hazardous asteroids, and sharing knowledge of astronomy through education and outreach, in particular, engaging with Native Hawaiian community. Las Cumbres Observatory is a network of robotic telescopes run by a nonprofit private operating foundation. The telescopes include the Haleakala Observatory in Maui, McDonald Observatory in Texas, Cerro Tololo Observatory in Chile, the Tive Observatory in the Canary Islands, the South African Astronomical Observatory in South Africa, the WISE Observatory in Israel, and the Siding Spring Observatory in Australia. Utilizing telescopes that are spread around the world greatly increases the opportunities to observe all astronomical events. The light from celestial objects can be sampled with greater frequency and for longer durations when observations are passed from one telescope to the next. Now, I'd like to welcome our guide on this cosmic journey, J.D. Armstrong. J.D., welcome.
Aloha. Well, thank you, Jamika. It's good to see you.
It's good to see you too. Thank you so much for allowing us to shadow you for this session. Um, Tell us a little bit about yourself.
Well, I am the Maui Technology Education and Outreach Specialist at the University of Hawaii Institute for Astronomy. Um, and I think that means that I'm the troublemaker around here. At least that's how I act. um, I work with a lot of younger scientists, middle school and high school students that want to do astronomy, tend to find their way into my office, and we end up working on various projects. Um, my PhD is from the University of Hawaii Institute for Astronomy. I have a master's degree in physics from Michigan State University, and my undergraduate degree was also in physics from Westminster College of Salt Lake City. And so, other than that, yeah, I don't know.
That's perfect, JD.
Okay.
So before we continue, I'd like to again welcome everyone. A few more people have joined us since we did our introduction. Again, my name is Jamaica Marshall, and I am very pleased to serve as the Shadow the Scientist Coordinator. We are shadowing in this session J.D. Armstrong of the University of Hawaii's Institute for Astronomy in Maui as he uses the Las Cumbres Observatory network of robotic telescopes. So first, JD, I know that we'll be going for about an hour. So is it okay if our guests drop their questions and comments in the chat throughout the session, and you can just get to them as we go along?
That would be great. Yes.
Fantastic. All right. So the title of your session is Chasing Asteroids. JD, tell us exactly what asteroids are.
Well, an asteroid is sort of what's left over from when the planets formed. So if we imagine that when the sun formed, it was this big cloud of gas that got compressed down, shrunk down, and then in the middle, there was this big ball of gas that became the sun. But around the outside, there was a disk because as this gas cloud collapses, kind of, it's like an ice skater pulling in their arms. And when they do that, they spin faster. And so you end up with a very rapidly rotating cloud of gas. And that sort of forms a disk. And that disk had hydrogen, but a lot of other elements too. They had all the iron and silicon, everything that the whole solar system's made of. And the silicates and metals kind of formed into asteroids. And they just have not yet made their way into a planet yet.
So not yet. So these are remnants of the formation of our solar system. And
Right.
contrary to what most people may think, asteroids are not located in just one spot like the main asteroid belt. There are actually asteroids
No.
right there in the around the outer planets as well, and around Jupiter, around Saturn, around Neptune. Tell us about those asteroids. Are they the same kind of asteroids?
Well, the asteroids in the outer solar system are going to have ices in them, so we refer to those as comets. So, or sometimes Kuiper belt objects or cloud objects. But but the main thing is that they're icy bodies. Things that are closer to the sun has been able to warm those objects, and the ices have evaporated off, have sublimed off.
Right. Yes, yes, through sublimation. That's right. What about these Trojan asteroids and the rings of Saturn, for example, and Jupiter and Neptune?
Oh yeah. Yeah, there is the Trojan asteroids. Those are asteroids that orbit the sun at a distance very similar to Jupiter's orbit around the sun. And they're trapped in what are called Lagrange points. So the simplest ones to think about, the simplest Lagrange points to think about are is the one between Jupiter and the sun. And so let's imagine we've got the sun and we've got Jupiter, and then we put a test particle somewhere in between. And either it'll fall towards Jupiter or it'll fall towards the sun. Okay. And the closer you get to Jupiter, eventually you're going to always you're going to fall towards Jupiter. If you get farther from Jupiter, you'll fall towards the sun. Well, that point between where it knows to fall towards Jupiter and the sun, that's a Lagrange point. And there are other places that you could put, your test particles, your marble floating in space, and it kind of wouldn't quite know where to go. And so those are Lagrange points.
I'd imagine that those of us who hadn't heard of Lagrange points before JWST learned about at least the L2, the Lagrange 2 spot,
Right.
as that was prepared to be launched and now is now doing amazing science. So there are multiple Lagrange points throughout the solar system.
Yeah, well, the Lagrange points are kind of affiliated with like a planet. So there's a Lagrange point on Earth's, there are Earth-Sun Lagrange points, which are points kind of around the Earth that orbit around the sun. You can also have a Earth-Moon Lagrange point, so Lagrange points between the Earth and the Moon. So yeah,
I
they're
see.
just orbital dynamics.
I love it. I love it. This is great. Okay, so before we move forward, we already have a question, and it was one that I was going to ask myself. And so this question is, yes, how does an object get pulled into Earth's orbit just for a couple of weeks and act as a mini moon before it leaves orbit again, right? And this is
Oh yeah.
regularly, where we have an object that'll come into Earth's orbit and will be around for a little while and be a second little mini moon. So first, how does it get pulled into Earth's orbit for such a short time? And then why does it not crash into Earth? Or does it just go on and speed by? What happens, JD?
Well, okay, so yeah, that you've gotten into some really potentially complex questions here. Okay, so why doesn't it crash into Earth? That's a little bit easier. So maybe I should share my screen. Should I share my screen?
Yes, go for it. Go
And
for
then
it.
you can see how terrible I am as an artist with my mouse. Okay. Okay, why is it not letting me? There we go. Okay, so we should have paint right here. Am I
Yes,
sharing the right screen? Yeah,
you
and
sure.
so, all right. So if you see my face in the video looking over everyone, that's because I've got another screen right up here. And so, all right, so let's see here. We need the Earth. So let's draw the Earth. It's a pale blue dot, right? All right, so we've got the Earth here. And you've got an asteroid. Okay. And so why doesn't it hit the Earth? Let's answer that first. Well, it's moving along, it's moving in this direction. And then it's falling sort of, if I can do this a little better than that, that'd be nice. Let's see, kind of falling in this direction. It's accelerating towards the Earth. Okay, so a component of it is this way, a component of it is this way. Now, if it's moving fast enough, it won't have time to accelerate and fall effectively this distance before it passes the Earth. That's how it doesn't hit the Earth. Okay, now an orbit is when it moves over and then it falls down a little, moves over, it's falling down a little bit, moves over, falls down a little bit, moves over, falls down a little bit, moves over, falls down a little bit, and you end up getting a circle or an ellipse. Okay, so it's not turning fast enough to hit the Earth, and it's turning fast enough that it doesn't ever get away. So this mini moon, it probably is my guess is it might be kind of spiraling in, or comes in and then kind of spirals out, makes several laps around the Earth before leaving. The other thing is it could have an interaction with the moon that slowed it down temporarily so that it could orbit the Earth for a little while, and then it'll get kicked out later on. And then I know that there have been other asteroids that have been presented as as moons of the Earth, so-called horseshoe asteroids. Those actually orbit Lagrange points. And so there was one that, okay, whoop, let's do, and everyone knows that the sun is really white, but I'm going to draw it as red because drawing a white sun on a white background, it would be hard to see. So there's the sun and the Earth. There's a Lagrange point somewhere on the far side of the sun that kind of the Earth and the sun kind of balance it out. And there was an asteroid that we observed. I observed it with some students over on Kauai, and it basically was orbiting around this this Lagrange point on the far side of the sun. And so we got to observe it before it got too faint, and then it's off, and we don't know what happened to it. We can guess, but we haven't been able to observe it to be sure.
Okay, so
All right.
so this mini moon is it's going to stick with us for a little while, but this is not an uncommon occurrence to have an object be pulled into Earth's orbit and stick around for a little while as a companion before getting booted out.
Yeah, it's probably going to be just kind of hanging around for a little bit. And let me see here. Okay, and then it will it'll eventually move on. I was just reading about this last week. A friend of mine texted me about this.
And so a follow-up question from Jim. So was this mini moon observed from a satellite? I assume it can't be seen from the Earth.
I think it might be able to be seen from the Earth. Let me see here. Let's go ahead and take a look. It sounds like it's a little bit of a diversion from what we were originally talking to.
That's true.
Talking about doing, but you know.
Okay. Is this a good? Is
yeah.
This
so, but
nice tangent?
I'm happy.
Back to it.
Yeah, it's a little bit tangent from what we were talking about, but hey, this is fun. So I'm actually beginning to think we might want to see about maybe observing this. Okay, so I noticed I went to Wikipedia. Go ahead.
I have a clarification. Jim says, no, I'm asking about the asteroid and the Lagrange point on the opposite side of the sun. The reference to was it observed from a satellite?
Oh, no, that was ground-based.
Oh.
So the one that I was observing, and we observed it using the Phelps Telescope North, which is part of Las Cumbres, the Las Cumbres network. It's the 2-meter telescope here on Maui. So we were actually able to spot it, and had a couple of students, or I had one student that actually tried to do a science fair project on it.
Okay, okay. And so now how could it be seen from behind the sun?
Well, the orbit was very, around the Lagrange point was very, very large. So, kind of was doing something like this. So it did approach the Earth, but then it continued around and ended up coming. I can't remember. It was like tens of thousands of years that it would go from just in front of the Earth all the way around to just behind the Earth, and so it would kind of orbit this Earth-Sun Lagrange point.
I see. I see.
I'd have to really go through the dynamics of that to give you a very good explanation. Let's see if there's a good Wikipedia article on it. Yeah, so
Jim said that was a more interesting answer than than was expected. So thank you, JD. That's perfect. And Wikipedia, yes.
Yes, and I actually do recommend Wikipedia. It's a good place to start off with. And if you ever are questioning validity of what's being said, um, there are all through, there are usually references that you can come down to the reference list. And then, so it's a good place to start. It's not a bad place to start. So, yeah.
Oh, and that's
So yeah,
that.
there. Yeah, that's what I'm talking about, is that sort of orbit like that.
Okay.
So yeah,
And so you were also going to, before we jump into what we had planned, you were also going to check Wikipedia for some details about this mini moon, right? Before we get back into your science.
right. Yes. Well, this mini moon kind of is it's an asteroid, so very much what we were going to talk about. Um, and so this is the one. I Googled it and found a news story that gave the numbering for the moon. And so whoop, not what I meant. Okay, so 2024 PT5 was discovered by Atlas at South Africa. And so should we see about, what do you think? Should we see about programming in some observations, see if we can get some observations of this?
Well, that's a great segue into what we were going to do anyway. Okay, so how about so I think everyone in the audience, you can raise your virtual hands. One of the things that we're going to do is give you several different options for targets that we could schedule program observations for. Because as a robotic telescope network, that's one of the unique things we can do and observe JD as he does and contribute to during this session. So let's see, raise your virtual hands if you want to go through observing programming observation for this mini moon. I'm going to raise both of my actual hands.
Yeah, so how about this? We'll put together a list and we can choose a few options and we can choose one or more. Should we
I
do
love
that,
that.
or do we want to just,
Yes.
yeah? Because why would anyone vote for no for anything, right?
Hey, that's true. That's true. We'll give you several options.
Okay. All right. So we're going to go over to the Minor Planet Center, and let's just see how reasonable it would be to observe this mini moon, or this second moon, or whatever you want to call it. So I just on the Minor Planet Center, I go to the ephemeris service. Ephemeris means like the coordinates versus time. And so this will give us a list of where the asteroid's going to be in the sky as a function of time. And we're going to want to observe this from Haleakala. We'll want a 2-meter for this. So I'm going to put in the observatory code for the Phox telescope north is Foxtrot 65. So F is in Foxtrot 65. And we want to go by hours. And I just want to get a little bit of an idea of how fast it's moving and how bright it is.
Now
Okay,
there are a lot of
go ahead.
numbers here. So maybe we could start at the top at this heading and talk
Mm-hmm.
about what everything means here. The right ascension, declination, sky motion.
Right. Okay. So the first part is this. This is the date. So 2024. There's year, month, day, and hour, and this is in universal time. So it's like Greenwich Mean Time, but don't do any of the daylight savings stuff. Okay. Right ascension is right here. So this is in hours, minutes, and seconds. Think of right ascension as longitude in the sky. If we imagine the sky being this dome around the Earth, this is like the longitude, the east-west measurement. And this is the declination, the north-south. And so plus 67 degrees means it's about 67 degrees up north of the celestial equator. So if you project the equator out onto the sky. Was that a raising hand?
Oh, no, it wasn't. Sorry,
Okay.
please proceed.
Okay, good. And so delta is, I think that's the distance between us and this mini moon. R is the orbital radius, the distance to the sun. And then I'm going to skip over to V. This is the magnitude. This is how bright the object is. And the next thing we need to know for observing is this sky motion, arc seconds per minute. So that's how fast it appears to be moving across the sky. And arc seconds is a small unit of angle. There are 60 arc minutes in 1 degree, and there are 60 arc seconds in 1 arc minute. So this is moving at about 2 arc seconds per minute. And with that magnitude, this would be difficult to observe because we would need to get an observation of, about almost 10 minutes. Something like, yeah, I would try to go for pretty close to about 10 minutes to get something this faint. And in that time, it's going to move quite a noticeable distance on the image. So we would get motion blurring. And so what we would have to do if we wanted to observe this is we would have to track the object, but and then all the stars would get blurred. So move the telescope so that it keeps the asteroid in the center of the image. But as it's doing that, the stars are moving. And so instead of the asteroid being streaked, the stars would be streaked. Okay. And looks like it's up for another couple hours. It's up till the altitude. So object azimuth and altitude. Azimuth is the direction, the compass direction. So north, south, east, west. Altitude is the angle above the horizon. And so we want it to be at least 30 degrees above the horizon because the telescopes don't like looking too far down. Partly because you're looking through lots more air, and so that's not ideal. And then the sun, well, we want the sun to be below the horizon. In fact, we want it to be 15 degrees or more below the horizon. Otherwise, it's just kind of hard to see anything. And they don't tend to open the telescope with the sun up because if the sun gets in the way of the telescope, yeah, that would be very bad, wouldn't it? So this is sort of the range of where, maybe 5 o'clock universal time to 7 o'clock universal time. That's sort of the range where we could actually observe this. And it would be possible. We would have to pull some tricks. Let's see how. And then moon phase, that's how bright the moon, that is to tell you how bright the moon is. It's getting very close to new. The distance, this is an angle in the sky between the moon and the asteroid, and the altitude of the moon. Well, it's not up, so that's good. Let's take a look at the map. This is an uncertainty map. It's going to show us how good the prediction is. Okay, that's pretty good. So it's within an arc second. So this is possible. It would be tough. I don't think we would get really measurable data. But I'm
Okay.
going to just go ahead and, yeah. I mean, we probably would get, oh, hey, there's a dot in the middle of the image, and look at all these streaked stars, which
Well,
at some point I'm going to do anyway. So,
well, what is another potential target we can choose from? Because I know we've been working together, which I'm really excited about. And so
mhm.
possibly maybe Ethel.
Oh yeah, we could look at doing Ethel. So let's put that on there. Did I spell that right? Ethel, Ethel?
Yes.
Okay. So Ethel, yes. Okay, let's take a look at that. Another one, I know that Apophis has been in the news a lot. We can
Yes.
see if that's observable. So there are three of them right there.
I think we have, yes, take that I out of Apophis.
What?
Perfect.
Yeah, good. Okay, so there's our PT5. Ethel. So this is one we've been and I think that we were going to look at this, get some observations daily for
Yeah,
Ethel. And so I'm just going to grab the magnitude and make a note of that. So magnitude 15, sky motion 0.46. So that would give us, we could observe that for, we could take an exposure, a single picture. We could leave going for 3 minutes before we really start to see much motion blur from on these smaller telescopes that we are using for this one.
that sounds a little bit better. Less
Yeah.
blurriness.
Mm-hmm. Apophis. This is again kind of faint, so this is probably not the best time to observe Apophis right now. It's
That's
moving it.
surprisingly faint. Wow.
Yeah, I know. Apophis is a big asteroid. It's a big one, discovered by Dave Tholen. And I think if we have time, I know that you and I have a bit of a story we can tell about talking to Dave Tholen over email about the discovery of Apophis. And
Yes.
Dave is such a great guy. He's kind of a character. He's really a neat guy. And other targets, we might actually go to the NEO confirmation page. And this is something maybe we talk about. These are asteroids that have been discovered generally by survey telescopes. And so the temporary designation is here. This score is like the chance it's, how likely is it to be a near-Earth asteroid? And so this is, very likely. I don't know that it's exactly percentage, but it's very likely. This is the discovery date, and you'll notice the day has a decimal part so that's including time. Here's our right ascension, declination approximately, and brightness. So this might actually be an interesting one to look at, but let's just go ahead and select all of them. And we're going to say, we're going to try to use the 1 meter network on Las Cumbres. So this Whiskey 85, W85 is for Sertololo. That's the ones at Chile, in Chile. Very nice site. And I love these 1 meters for observing these, doing the near Earth asteroid recovery, because you can usually get on sky pretty quickly. Now I know this is a new detection, because this was, I was looking at this list earlier, and I do have a couple of observations that we might be able to look at. Okay, so I need to stop and explain what just went through my brain there, don't I?
Yes,
So,
that'd be great. And we have a suggestion maybe Vesta could be one of the objects we potentially consider putting observation in for.
Oh yeah, I like Vesta. Vesta's going to be really bright if it's yeah. And wasn't it Vesta that had that bright spot on it that they were going, what is that?
Oh, I'm not sure. Maybe someone in the chat knows. Although I'm sure you're
Yeah. I'm not sure that I'm right because it's one of those one of those thoughts that's in the back corner of your brain and has a bunch of cobwebs around it. Okay. Vesta, yes, this is magnitude 8.3. It's moving at a speed of 1.2 arc seconds per minute. This will be easy to spot. So magnitude is kind of backwards and it's logarithmic. So the story I tell is that Hipparchus was bored one day because I guess his internet was down. Hipparchus ran with Socrates and Plato, so you know. Okay, so there's my little joke in there. But anyway, he wrote down a list of stars, and he started with the brightest stars were first magnitude, and then the second magnitude stars were the second brightest. And so we ended up with a system that the bigger the number, the fainter the object. This is so bright. If it were only 5 times as bright, we might stand a chance of seeing it with the unaided eye. So I mean,
wow.
it's getting close, yeah, 5 or 6
Okay.
times, something like that.
So
Um,
could Vesta be one of the as I see that, wow, we only scheduled
mhm.
this session for an hour and we have like 23 minutes left. Oh my goodness.
Oh, geez,
Okay, so
yes.
let's choose 2 objects. Can Vesta be one of the options that our participants can?
Um, well, let's see here. The altitude of the object is, it seems to be up when the sun is up. So this is
Uh-oh.
just the wrong time of year, but that's a great suggestion.
Okay,
So
maybe in another
whoever,
session.
yeah, yeah. So thank you for that, Johannes. Yes.
Okay, so let's see. What are 2 options we can give our participants to choose from for putting in some observations during
Okay.
this year?
Okay. So we could try the mini moon. That'll be yeah. We can do Ethel and maybe program in some observations. What Jamaica and I are doing with Ethel is we're helping measure the rotation rate, and maybe that'll be an upcoming episode. Yeah, there's a teaser for you. Is that good?
That was
All
perfect.
right. This one, this is a really good target if we want to do a near Earth asteroid. Wait. Maybe I may have to take that back. Object altitude. Well, no, this is not such a great object. It uh, doesn't quite get, it's too close to the sun. Uh, let's see here.
Oh,
Let's change that to, oh, wait, let's see here. Yeah, it's a little bit too close to the right ascension is too close to the sun. So, so the east-west position is aligned with the sun. So it'll be up when the sun is up.
oh, when the sun.
Yeah, otherwise I would really strongly suggest that one. This is a possibility. And so one thing I think about a little bit, I shouldn't think about it too much, but I do. This is starts with the letter A. So that's Atlas. That's a University of Hawaii project. And so and this is P for Pan-STARRS, also a University of Hawaii project. And so I'm usually a little more inclined, all things being equal, I would probably select a Pan-STARRS or Atlas object first. Um, Some of the lesser known ones, if I don't recognize the code for it, I might skip it, even if it looks like it's a good one, because every now and then you get these surveys that don't give great predictions. This is a Catalina Sky Survey. Don't tell anyone from Pan-STARRS that I said this, but they're a really good survey too. There's always this kind of, we Pan-STARRS folks pay attention to how they're doing. Skimming down, and I'm just looking at the brightness and sky motion, doing quick calculation in my head to see if there are any that really stick out that I might want to observe. This one might be, let's see. Yeah, there's a fair amount of uncertainty for that one. But I would keep on doing this. And I would get until I got to the end of the list. But since we are running a little bit short on time, we'll do that. The other thing is I've been, a couple of asteroids are possible that I've discovered, and we could look at one of those.
Oh, you know what, JD? Yes. Well, okay, first, Yuli has a question from a sixth grader who's asking, are you, because of your last name, are you related to Neil Armstrong?
I get that a lot. Yeah. No, I'm not related to Neil Armstrong. And my mother actually has looked at the genealogy, and so we're pretty sure I'm not related to Neil Armstrong.
Oh,
But that would have been so cool. Yeah.
oh wow. Thank you for that question. I'm gonna make an executive decision and say yes, we want to do follow-up observation of the potential asteroids that maybe you have discovered. Yeah, let's do it. Let's do it.
Okay. So let's really quick. Let's do. So I'm going to go to the Minor Planet Center database search. Okay. And these are ones that they've actually kind of declared, hey, there's really an asteroid here. We've gotten enough observations. So I'm going to kind of go through really quick and see. We'll try to make sure it's one that I either definitely have or probably observe first. Let's see, QC6, I think that was, so yeah, so I've got it at 924. I don't think this is one of mine. So this is, keeping notes of what, oh no, this probably is mine. This might be a good one to observe. Let's also look at the interactive orbit sketch.
Oh, I love
Some of these get kind of cool. Yeah, I know. That's why I go here even if I don't need to, because it's cool. Okay, there we go. And so this is the asteroid's orbit. Here's Mars, Earth, and so you can kind of rotate that around and look at it from different positions. Yeah, and let's see. Okay, that's just left, right. So that shows you a little bit of what it looks like. This might be a good one to get because of the fact that I'm hoping that they will link back to this observation that I have here, which was on August 30th. And that is, that's before the first observation used. So what I'm kind of probably doing is trying to get this discovery from somebody else. Most
Oh,
likely pan stars, because every time I see someone else grab mine, it's pan stars.
oh
All
wow.
right, so that might be a good idea. So we'll put that one on the list too. And so who wants, so do we want to do a vote here?
Yes. Yes. So tell us
Okay.
the two options. This is the first one.
Okay, so that's the first one. What do you want for the second one? I'll let you choose if we want to do a NEO recovery, Ethel, or mini moon.
Um, okay. Oh, we have mini moon, we have QC6. Yes, put your suggestions in the chat, please. Okay, another QC6. Okay, yep, QC6 again. Oh goodness.
Okay. Well, let's go ahead and do this. I did do some observations earlier today, and maybe we'll take a look at those.
That's right. That's
I
right.
already, yeah. But yeah, okay, so we'll go with QC6, and we're going to want to get ephemeris service to get the magnitude and sky motion. And let's see here. Magnitude 21.3, sky motion 0.54. Okay. So yeah, that'll be okay to do. It'll be a little bit on the faint side, but doable. So this is the Las Cumbres Observatory web interface. You do need an account to access this. And proposal is just the proposal. It's the group of time, the account, the bank account of time. IPP factor is just a priority factor within the proposal. They have different classes of instruments. So we want to do a 1 meter, a 40 centimeter telescope just is not big enough to really see it. So we need that full 1 meter of collection area. For this, we can go 180 seconds before we start getting motion blur. These are various colored filters. And so Bessel B, as in Bravo, filter lets blue light through. I is an infrared. R is red. What we want is something very wide. This covers most of the visible spectrum. Okay, this is the widest filter they have, and we don't want to be losing any light when we're just trying to find the location of a faint object. So this is the name of the object, but if I go in here and I click on non-sidereal, and then I give it the name of it, it's going to come up with these orbital elements that have been determined by the Minor Planet Center. So these are things like the eccentricity, how elongated the orbit is, the semi-major axis, how large the orbit is, and mean anomaly, various things like that. So, and okay, we come down here, and here's our visibility chart. I'm actually, don't tell the folks at Las Cumbres that I am going to do this, but I'm actually going to try and encourage the system to observe this from Cerro Tololo. So this orange line, the lines in this show when the object is visible. Whenever there's a solid line, that's one of their telescopes that can observe that target. Up and down is like how far up in the sky it is, how close to looking straight up. And so, and when there's a solid line, we can observe. I think I said that already. So we're going to go to the 28th at 6 is the latest we're going to go. And I'm going to go ahead and say, well, I don't want to look through more air mass than 1.3. So I want to kind of try to point it up. 1.2. So we don't have a lot of time to get these observations because this is now. Okay, there we go. Yeah. Okay, we'll try that and see if that works. And then we're going to do a dither. So what this does is it moves the telescope between each image by a small amount. And that is to make, oh, that's annoying. Should be able to make a dither on this. Okay, something went wrong. Home, submit observations. And I'm just going to go screaming through this as quick as I can. The dithering, basically, there's sometimes the flat field doesn't eliminate everything that is on the it doesn't eliminate all the blemishes. And so it can look like there's a little dot of that's moving, and by dithering, the motion of that dot can be distinguished, basically. Okay, let's see if it'll let me dither.
Oh
Does
no.
not like to do the dither pattern, so we go back to the minor planet center and get the position. Okay, there's W85. So we're just going to basically do this the hard way and enter some coordinates in here. Here we go. So instead of doing sidereal, we're going to do non-sidereal and just enter these right ascension and declination coordinates. And we're just going to call it good. Hopefully we will. Okay, now let's try generating dither. Unable to generate dither. Okay, then we're going to go back to non-sidereal and just tell it to take 4 images. Apparently there's some kind of glitch that's going on, and it's probably related to the use of sidereal. But everything looks good. I'm not getting any warnings. But one thing that's weird is it usually gives me an estimate of time. So everyone cross your fingers for me. We're going to submit this. This is the first time I've ever seen this happen. And I've been
Oh.
using the system for years. I'm going to start over. Oh, I see the problem. Every now and then you have to refresh your login. And so I'm going to do that real quick.
Oh, okay.
Okay, that's looking better. Now these are all observations that I recognize. Oh, these are observations, by the way, that are being taken by Wailuku kids, some students at Wailuku Elementary. If we get a chance, we'll talk about those. Okay, this is looking better. Dither grid. Okay, let's see if we can dither. There we go. There's our dither pattern. going to tell it okay. And I'm going to go ahead and submit that. This will be about 14 or 15 minutes, 16, nearly 16 minutes of telescope time. Time well spent, in my opinion. And so there we go. All right.
Yay, that was great.
Okay, so what are the requirements to get time on this telescope? Well, for students in Hawaii, you actually can work with me and I can get you observations. And I believe the person asking that is a student here in Hawaii. Hi, how you doing? And if you're outside of Hawaii, then you would you can apply. You can submit a proposal. If you're a teacher, the 40 centimeter network is very usable, very accessible. And the other thing you could do, there's a sister project called Photon Ranch, which is up and coming, and this is being built with the idea that students can learn how to do real research. Very cool project. Notice it's under the Las Cumbres branding. And so there are several sites around the world, and you would have to get an account there. And they'll have activities that you have to do. And then you'll earn time by doing activities. Okay. All right.
We have a request to see if we can stay on to get those first images, but how long would it take for those observations to come in, JD, the ones that you just programmed?
The ones that we just programmed, they might come in very quickly. They might not come in at all. Let's see. They have not yet made their way onto the schedule. It might mean that we did not give it a very much time to get going there. Let's see. So if they're not complete by 5:50 Universal Time, it's now just approaching 5 o'clock. If they don't complete by 5:50, they're not going to attempt them. They may get this on the schedule, may not. Depends on how. Yeah, depends on how busy the observatory is. Let's do a scheduler visualization and see how heavily requested time is right now. Might be able to squeeze it in here on Dome. So there's a chance that we'll get this in another 10, 15 minutes.
Okay.
That it might start coming in. I'll go ahead and share with you some observations that I did get earlier today. This is a different asteroid that it's a little less certain that I might have gotten that I might get discovery credit on this one, because Pan-STARRS is really good at spotting everything. Sometimes very annoyingly so, but I guess that actually is a good thing for them. Okay, so these are some images, and this is Astrometric. This is a program that is designed to look at the stars, find very precise locations in the images, and then help you mark where an object is. And I think this is not because I am that sharp at catching it. I think this little guy right here, that might be my object. So I'm going to go ahead and mark that. Okay. So this, yeah. Yeah, I still look at it and go, wow, I'm surprised I caught that. So what I did here is I pushed this button, which they go and look at known targets, and this is a way. the closest known object is about 4.5 arc minutes in right ascension and about 8.8 arc minutes in declination. And so this is not that target. That's not what this is. So I'm just going to call it, just give it a temporary name. Isn't that clever, calling it temp? Okay. And so I would go ahead and mark this. And that third image, I don't know that we've really got it. I think there was another, yeah, there's another asteroid here. Let's go ahead and mark that. Okay, now this one, like I said, I've looked at these images just briefly, just enough to find that one that I wanted. So this is a known asteroid. It's very close to the position that's predicted, and even the magnitude is actually pretty close to what we expect. Well, it's brighter than we expect, but that's pretty certain that that's the object. So I'm going to copy that. We'll do that. Do that. Do that. All right. And then we'll go back one more time and see if that other asteroid is being observed or not. Sound good?
Yes, let's do it.
Okay. So there we go. And then this shows if I view MPC report, so it's measured the positions that I've asked it to and kind of stored them here. And we're going to go check and see if we are in luck. Okay, yes. So 5:22, the observations will begin. So that's a couple minutes away. What I'll do is I'll make an animated GIF image, and it'll probably be just a part of the image, but I'll make an animated GIF image of something moving, of one of the asteroids. Does that sound good?
That sounds fantastic. And Elizabeth asks, are the telescope requests fully automated, or are there humans confirming them?
For Las Cumbres Observatories, the requests are fully automated. This is a robotic system. The only humans that have seen these requests are in this meeting. Yeah, you and I. So Kaua. Right. So and then the telescopes don't have people at them, and they don't have remote operators. They're purely robotic. They do this by themselves, which is the really cool thing about one of the really cool things about Las Cumbres. So